Right now we've defined important quantities. We've defined the temperature, and temperature is our ultimate measurement, if you will, because it tells us everything about thermodynamics. Right? The thing that we saw when we let that piston go and we let the energy transfer through the piston and allow the piston to settle in our little box that's separated, we saw that the piston stops when the temperature on both sides is the same. Right? This idea of transferring heat or doing work, moving energy from one section of your system to another, the way that we track the way that that equilibrates is through the temperature. And if you've got two different subcompartments of your system that are in equilibrium with each other, they're in true equilibrium with each other when the temperatures are equal. Right? Temperature tells us everything. And we're going to explore temperature a lot in this class and what we can do with it. And so, but one of the things that we're going to have to work with is, again, let's just write down our equation one more time, right? The fundamental equation of thermodynamics. That when we move a system a little bit, right, let that piston jiggle a little bit, just an infinitesimally small amount. We're going to change the energy of the total energy of the system U, and that energy is, the change in energy is kind of fragmented or segmented into little parts, right? Different types of motion, different types of uses of energy. One is, of course, heat, right? The entropic contributors, right? We call this heat traditionally, sort of. We'll see what heat actually is, but this represents the motion of heat, transfer of heat from one part of the system to the other. We'll define that more carefully today. I'm sorry, yes. You know, so the other class, they have a beautiful screen and they can see that red. Can you see this pink a little better? Not really. All right, so what about this green? How does that green look? That looks pretty good. Yeah, maybe close it. I don't think that's going to solve any problems.
No, I just can't see anything.
Okay. That's better, yeah? Okay, so no red. If I use it again, just yell at me. All right, so we got this heat energy, if you will. We'll have to define what heat is, and we'll do that in actually about 10, maybe 15 minutes. Specifically what heat is. We have this idea of work, mechanical work, volume, pressure volume work. Right? This is the energy used to fill the box. Right? This is work in the same way that Physics 1 talks about work, right? Motion, forces applied over a distance. Right? This is work. In particular, it's pressure volume work. All right, we're going to look at pressure volume work again. Actually, we're going to spend pretty much the entire lecture on this part of the analysis. And then we're left with the remainder, which is the chemical part, right? Which is a sum over all the components of your gas, right? If we have air, there's nitrogen, oxygen, carbon dioxide, argon, so on. There might be N components of your gas. And the way that the energy changes as the component number changes, the relative concentrations is the chemical potential, mu, and it's proportional to the change in the number of molecules of that component. Right? This is called chemical work. So far, we've basically set this to 0, the chemical part, because we've only been dealing with a box of a single gas, right? And most of the boxes we've been looking at are ones where the molecules can't leave. Right? So eventually, we're going to have to think about when molecules leave. Eventually, we're going to have to do a reaction, right? Which is you're going to have a vessel with some gas or liquid in it, and the cap is open, the top is open, right? We're going to have stuff maybe leave. Right, so we're going to have to think about chemical potentials in this context where you may have gases evolve from your reaction escaping. And of course, what happens is when you have a gas evolve from a reaction and it escapes, that's actually entropically favorable and it drives your reaction forward. So the chemical potential of these evolved gases from reactions drive reaction forward because they apply chemical work and drive the system towards equilibrium. All right, so we'll look at those things more carefully when we get to it. And the example we're going to be looking at today is kind of our first case. So one of the advantages of this again is this tells us everything we need to know about the energy. The problem is that if we adjust the energy of our system in an arbitrary way, right? We make a change in du, that energy is going to partition itself into all three characteristics. So you don't really know how much is going to go into heat, how much is going into work, and how much is going into chemical work, unless you really pin down the constraints and the system itself. We have to think about how the box or the system or the process is designed to really think about how the energy gets divvied up into these little compartments. Okay, it depends on the system. But we know that the change in the energy of the system is always going to be a sum of all these terms. We just don't know how much goes into one or the other. Right? And that's kind of what we're going to do today, is make those constraints. Right? We're going to create a box or a system or a process where we make a constraint to the system. Say we fix the temperature or fix the pressure. And then we'll be able to simplify this equation and get a good sense quantitatively of how the energy is flowing through the system as a part of whether it's heat or work. Right? We can actually measure how much is work and how much is heat. Right? And that's going to be really useful for us because, right, eventually we're going to want to think about how energy is created in chemical reactions, right? And so we're going to have to think about how much energy is being put into heat from a chemical reaction and how much energy can we use from a chemical reaction to do work, right? For instance, if you had a combustion engine, right, you want some of that energy that's created from your combustion to drive the wheels. That's doing work. But if the reaction just gives you heat, it's all completely worthless heat. It doesn't drive any work, you're not going to drive your wheels, you're just going to blow your engine up and nuke it, right? So a balance of these things are important, and the constraints that we put on the system enforces the energy to go a specific way. Okay? And so every time we design a process, we're going to want to think about the constraints we can make so that we can control how the energy flows from point A to point B. Okay, and so the first example we looked at today, or yet last class, kind of at the end. Now, is this purple good? Let's see. Yeah. All right, I'm going to use the neon green then. The first kind of process we're going to look at is what's called, and this is what we finished off last class with, is an isothermal process. All right, and again, just a little bit of Latin and Greek, ancient languages. Iso means the same, and thermal means heat. Right, so this is a process, well, and we'll think thermal temperature. This is the process where the temperature stays the same. Okay, so the constraint that we apply to this system is that the change in temperature is 0. Okay, so the temperature is fixed. You do anything to the system, it may generate heat, may generate work, but the temperature is not going to change. Right, a really good example of an isothermal process is combustion. Right, if you have one of the parts of we'll talk actually, I'll have a small lecture about the Otto cycle, which is the 4-stroke engine cycle with a normal combustion engine. One of them is a compression step where you compress the fuel, right, the gases into your combustion chamber, right, into your cylinder wall, and that cylinder is kept isothermally because it has a jacket around it with antifreeze. And one of the keys to maintaining stability in an engine is that you can do this compression isothermally so that your engine doesn't overheat, one. And so that's why one of the reasons why we antifreeze is that it keeps the piston walls, the surface of the box, constant heat, right? So that the temperature is always constant. And we'll see the consequences of when you don't do that, what happens when we get to it. There are, in combustion process, there's more than just isothermal processes. So there's other conditions that we have to set for the other strokes as well. So we have to talk about this before we can talk about combustion. And another really interesting one that we'll talk about as well, that's similar to an isothermal process, is the process of creating energy in the sun as well, which is a very interesting form of thermodynamics, the sun itself. Okay, so here's the way we're going to work on this system. Here's a classic, this is kind of the prototypical example of an isothermal system. And again, this is a good one. You'll immediately see, if you're into cars, you're into combustion, if you've ever thought about an engine, you'll be like, well, this looks just like a cylinder of a combustion engine. The idea is that we're going to have once again, a box. And in that box, we're going to put a piston that's movable. All right, and this piston, the piston itself is closed, so no energy can transfer through it. All right, and the piston's adjustable. All right, so there's a little dude over here. I'll give him a smile. He can push and pull this piston, and it's sealed to the environment, but the important thing is that this piston, the walls of the cylinder are diathermal. You can exchange heat. Okay, so the way I'm going to represent exchanging heat are these little squiggly lines that mean that you can exchange heat in and out of it, right? It's a diathermal cylinder. Okay, and inside of this little compartment that's sealed where the piston is pressing against it is a gas, okay, at some temperature and pressure. All right, so let me draw my little gas in there. You've got some gas in here. All right, and our little homie, he can push and pull this. He can either let it expand or push it any way he wants. He can just jam it shut. He can move it really slowly. He can pull it out really slowly. He can release it really fast. He can do anything he wants to it. All right, we'll look at all those cases. The most important thing is we have to maintain an isothermal condition. So what we're going to do now is we're going to surround the cylinder with a water bath or some bath that keeps the temperature constant. All right, so the thing is surrounded by some environment. It could be the air, right? It could be a water bath, right? We have a constant temperature bath surrounding it. Right? Maybe it's a little hot bath that you make in the lab. All right? And the bath is always set so that the temperature of it never changes. Okay? It's a fixed temperature. All right, and I'm not going to go through the derivation again. We went through the derivation last class, but I'll just give you the result. We wanted to consider how the entropy of the system changes. Right? How does the entropy of the system change as we move the piston back and forth? All right, so the interesting thing is what we're going to do first. So the first case we're going to consider is what's called a reversible expansion or compression. Right? And what a reversible one is where our little homie, he pushes, we should give him a name, but I'll just call him homie for now. He gives it a little push, just a tiny little push, and then he allows the system to equilibrate. All right, so that the temperature never changes. Okay, we'll talk about what happens if he pushes it really fast and really hard. We'll see what happens. But the idea is he's just going to slowly move this container infinitesimally small steps, so that in between steps the system stays in equilibrium, never drives it out of equilibrium. Right? So the system stays in equilibrium. So the motion, the piston moves slowly enough so system stays in equilibrium. And what does it mean to stay in equilibrium? It means that the temperature inside the piston is always the same as the temperature outside the piston. All right, that means that as I said, the consequence here is that the temperature of the piston is the same as the temperature of the bath always. Okay. Well, consider when he doesn't do it reversibly, when he just jams it shut, what happens? All right, we'll look at that graphically and we'll think about it intuitively as well. Okay, so if the system's always in equilibrium, we can write a really, really nice constraint, which is that the total energy of the system, the change in is zero, right? This is equivalent to saying that du, which is the total energy of the bath plus the piston, is equal to zero. Okay, so what that means is that for every bit of energy we put into the bath by pushing, for instance, every piece of energy we put into the piston by compressing it, we'll see that requires a positive energy. that's compensated by a loss of energy in the bath. Okay, so every time we put energy in, that energy flows out and equilibrates with the bath, right? So the total change in energy will be 0. As always, it always is. Okay, and the solution that we get, if du is equal to 0, then the big thing that we get here, right? So our thermodynamic equation. This is oh, I can't use that color. I'm sorry, guys. Probably like he's not even writing anything. So our thermodynamic equation that governs the behavior of this system is that T times ds, temperature times the change in entropy, is equal to the change P times the change in volume. Right? TdS is equal to P dV. What that means is that for all the, right, where we're going to start changing the volume of the box, either putting energy into the system or pulling it out, that will be compensated by a change in entropy, equal and opposite. Right? And again, that's just a consequence of the fact that the temperature is the same everywhere. And so what that means is that all work is compensated by an equal increase or reduction of heat in the system. All right, and again, we worked through this equation. We assumed an ideal gas. Right, ideal gas. And we got this lovely equation, very, very simple equation, which says that the change in entropy upon moving the volume by compressing or expanding is equal to the number of moles of the gas times the gas constant times the log of the volume ratio, the final volume divided by the initial volume. Okay, so let's think a little bit about what this equation tells us. All right, so let's compress the system. All right, so we're going to push against that. Now it should be logical. If you've ever blown a wheel of a bicycle tire up, you should understand that you have to put energy into the piston, the pump, to pump the air up, right, to compress. Right, so we should expect that compression takes energy, right? And that should make sense, right? You're trying to push this piston against a gas, which is, has a pressure. It's resisting the force of that push. So you have to apply a positive energy to the piston to compress the gas. So how does the entropy change upon compression? Well, if we're compressing, that means the final volume is smaller than the initial volume, right? So this ratio is going to be less than 1. Right? VF is greater than VI. Or sorry, VF is less than VI. So let me just write that. So the first one is compression. All right, so that's going to be VI is greater than VF. Okay. So that means then that the ratio of the pressures, VF over VI, is less than 1. All right, it's positive, obviously, because they're both positive, but it's less than 1 and greater than 0. And so let's go ahead and plug that into our value here, into our equation here, right? So we have the log of a fraction less than 1. Right? If VI is less than V1, what I can do is factor out a -1 and get n minus nr log of VI over VF. Right? That's just a classic log identity. I'm just factoring out an exponent of -1 and flipping the sign. Right? So now I have a positive number here, positive ratio. VI over VF is greater than 1, right? Because the initial volume is bigger than the final volume. So I have a pot, right? NR is positive. N's a mole, for instance. R is 8.314. And then you have a log of a positive number. So this whole thing is positive, but there's a negative sign. Right? So for compression, what that means is that the entropy is negative. For the piston. Right, so by compressing the gas in the piston, we're reducing its entropy. You're going to do on problem 4 of the homework. We'll talk more about kind of the concept of that today. You'll prove that when you expand a gas, in fact, what you're going to do is directly calculate it, the entropy change, when you go from a volume of 1 to a volume of 2. You double the volume, your entropy increases. Okay, so this is an entropically negative process. You're ordering the gas inside of it. That should make sense, right? That the gas has less place to move, so it's moving around less. It's more tightly constricted, and so there's less random motion, so the entropy drops. Right? And what this means again, if the entropy is less than 0, right? This means that the piston can't spontaneously compress. Remember something that happens like remember the first problem we looked at, which was when the piston was allowed to move freely and adjust where it wants to based on the energy difference and the temperature difference between the two compartments. This compression is delta S equals less than 0, which means that it doesn't happen spontaneously. It means that you have to apply energy yourself to do it. It won't do it on its own. Right? So this is something you have to apply a positive amount of work to from yourself. You have to expend your own energy to get the gas to do this. Likewise, if we do it the other way, expansion, and again, I'm not going to go through the math here because it's just the opposite. Right now, VF is greater than VI. And this, of course, means now that the entropy change is greater than 0. Okay. Well, that means that what that means is that if the system is compressed and our homie lets go of his piston, the expansion of that piston is spontaneous. It's just going to occur if the piston is allowed to move. Right? The gas wants to naturally expand. Right? And of course that makes intuitive sense. That the gas naturally wants to expand, right? Because that's exactly what happens, right? Think about a balloon, right? If you blow a balloon up with your mouth and you pinch the opening, the hole, right? So you've put in energy to compress it, right? You've increased the pressure inside the volume's also increasing. But think about it now, when you've got it blown up to some pressure, and then you let it go, what happens? Well, it doesn't compress further, right? It expands, right? All the gas releases, and the pressure inside the balloon equilibrates to the atmosphere, right? Gas wants to expand, right? It wants to press out as far, it wants to fill the space. And filling the space is always entropically positive and therefore spontaneous. It always happens. Right? It happens without us even trying. Okay, so already, just with this simple equation, just a little thought, we've already recreated kind of baby's first gas chamber or something like that. I don't know. But again, these are kind of really intuitive ideas, but they're formulated in a very kind of rigorous way. This entropy, the sign of the entropy of the process tells you something about the natural order of how things progress. Something that's positive entropy, the process of positive entropy is going to want to do that with or without your help. It doesn't need it. And then negative entropy means you're going to have to put energy in to do it. All right, so let's kind of dig into this a little bit more. All right, kind of do a little bit of analysis to see what's really going on here. I'm only talking about entropy here, but how is energy flowing in and out of the cylinder into the bath? Right, how is the energy actually being exchanged? Right, this only kind of tells us a little bit about what's happening to the gas, and we have a sense of what's spontaneous and what's not, but how does energy flow in the cylinder and how does it pull it out of the bath? Is it okay if I go to the next page? Does anyone keep writing? Real good? Okay. All right, so let's remember that our equation, right, so for isothermal, we have du, which is equal to 0, which is equal to TdS minus PdV. But I also wrote down, we also discussed a little bit last class about a different way to write this equation, right? This is the Gibbs way of doing things. This is the Connecticut approach to thermodynamics. But what would Joule, the Britishman, what would he say? Well, he would say that du, which is equal to 0, is equal to the sum in the changes of the heat, right? This is heat, plus the changes in work, right? Joule didn't have any concept of entropy at the time. Entropy hadn't even been invented or discovered at this point. Right? So he only saw things as heat and work. Right? And that makes a lot of sense. He's an empirical person, and he recognizes the difference between, you know, a motor and a hairdryer. Right? They can both provide energy, but they provide it in two different ways. Right? Work and heat. So, but the nice thing is that we can compare these equations directly. Right? Oh, sorry, that's the wrong color. Right? We can see that TdS is like dq, and PdV is our work function, minus PdV is our work. Right? So from Joule's point of view, the change in work is equal to minus the change in heat, right? Because du is equal to 0. Right? This just means that dq is equal to minus dw, right? And that's equivalent to saying PdV minus PdV is equal to minus TdS. Right, so we have, in the isothermal instance, we have a logical connection between intuitive ideas about energy and a more abstract way, right, the Gibbs way of thinking about energy. Right, the work has something, the change in work of your system is the pressure, the volume, the change in the volume that you're making, and the heat release has something to do with the entropy. Now notice that with this term in particular is okay, it's pressure times volume. But here, as I said, we often I talked about how entropy has something to do with heat. But if you notice, dq is proportional to temperature times entropy. So the classic definition, therefore, is that the entropy change is defined as the change in heat divided by the temperature. All right? So what entropy is that, okay, so let's say, for instance, you're at 300 Kelvin, okay? And you're at 300 Kelvin, and you've done this compression or expansion, and you've transferred some heat in and out of the system. The entropy changes that heat energy per unit temperature. Okay, so if the entropy is the heat content of your process for every value, every unit of temperature that you have for your system. Okay, so if your system is at 1 Kelvin, you'll transfer your entropy change for an equivalent amount of heat will be 1/300th of 300 times what it would be if T was 300. Right? If ds is the same for both temperatures, dq is the same for both temperatures, then the entropy changes consequently vary based on the difference in temperature, right, by a ratio. Okay, so entropy is kind of like a specific amount of heat. Right? The units of this are not joules. Right? The units of entropy are not joules, but joules per Kelvin. Right? Joules per Kelvin. Okay, so if you ever want to, if you've measured your entropy and you want to know how much heat is being transferred, you have to measure the temperature. Right? And then when you multiply ds, the change in entropy, by temperature, you get the amount of heat. Okay, so entropy is like what we call a specific heat. It's how much heat is being transferred per unit thermal energy, which is what temperature measures. But this equation also has a really interesting consequence, is that the amount of work we put in is compensated by a negative change in heat. So just give me just a minute. I'm gonna copy this piston back over because I want to use it. Your job is to think of a name for our friend for next time. Otherwise, I'm going to start picking random people in here and calling them you. So here's our piston. Let's now imagine that our broken homie here, I need to fix his head, is going to push this, right? He's going to apply some work. Right? He's going to apply some work to the system by compressing the piston. Right? So every time he does a little step, so every little push with work dW, that I'm going to call him thermo-homie. Thermo-homie makes. The system compensates by releasing an equivalent amount of energy as heat. dQ. Okay, so he puts in dW, right? So he's going to put a little bit of work, and the system responds in kind by releasing an equivalent amount of energy. So I'll do it like this, dQ. Okay. So the system, right, that's how it maintains thermal equilibrium and keeps the temperature constant. For every bit of energy you put in, it releases an equivalent amount of heat to compensate. And the opposite happens when you expand. If thermo-homie lets go of the piston and allows it to expand, the system will bring in heat to drive the expansion, which will be returned as work out. Right? The piston's going to provide work in this direction as the system brings in heat to expand. Okay? You just flip the signs. All right, so the bath, so it's not like, the idea is that you're not, in reality, you're not really putting energy into the system. You're doing a little bit of work, but that energy is not getting absorbed into the material. It's being compensated by a release of heat into the bath. Okay, so there's no net energy change, right? dE is 0. There's no net energy change. Every unit of work W is released as a unit of Q. So there's no net energy change. Okay? But again, we can manipulate the system, right? We can change its conditions, change its entropy, but we don't change the energy at all. Okay, nice consistent system. That's a really nice, again, it's a really nice place to, this is a really common way to do anything in process chemistry, if you will. You know, in chemical engineering, we do isothermal compressions and things all the time because in the end, you don't really expend any energy, right? Because imagine that you do this work, right? You have some motor that expends this work out, okay? Expends this work and compresses it, which then the system releases heat into the bath, as that energy is heat into the bath. Well, that might cause the bath to heat up a little bit, but you could siphon that extra heat out into something else and recycle it, right? You could use the heat that this creates for another job somewhere else. Right? And that's how basically all industrial mechanics are, gas, compression and, natural gas pumps and all sorts of things work. Right? That you can in some ways get some of that energy back as a refund, right? Because because whatever you push in gets transferred out, and you might be able to siphon some of that away for another process. Right? So it's somewhat of a very efficient, it's an efficient process. We'll have to ask the question how efficient it is. It might not be 100%. Right? We're not going to be able to, as you might imagine, for every unit of work we put in as releases heat, we can't recycle 100% of that back into work. All right, we'll have to consider that in a little bit. All right, so we're going to lose some. Right? It's not 100% efficient. If this were 100% efficient, we'd have a perpetual motion machine, which of course is not real. It's impossible. So we're going to lose some of that heat to the surroundings. There's nothing we can do about it. But ideally, you could think theoretically that this thing can run forever. Right? You could just keep doing this over and over again. Right? That's kind of how an engine works, right? The engine, of course, doesn't work. A combustion engine at best is only about 45% efficient. But theoretically, if you make a 100% efficient engine, it could run forever once you get it started. Questions? Okay. So let's look a little bit at this graphically. So, and the reason why I want to do that is because what we haven't considered is if thermohoming's really lazy or kind of pissed off and he just jams it shut. Right? Instead of doing a reversible motion, he pushes it closed so fast that the system can't exchange the heat rapidly enough. Right? Think about this motion of heat and energy having some time scale. Right? It takes some time for the energy to dissipate into the bath and then be recirculated. Right? Imagine he shuts this close fast enough that it's faster than that time scale. Right? And I think the best way to look at this approach, right, to think about what are the differences in compressing something like aggressively versus reversibly. And the way to do that is to think about it graphically. So the important thing that we're going to look at again, let's just again go back to our equation. We had that TDS is equal to PdV. Right? And then we can use the ideal gas law, which is that P is equal to nRT over V, which says that TDS is equal to nRT over V dV. Okay? And again, this is the change in work. It's a change in work. Let me get my notes. Right. Okay, so what I want to think about now is I want to think about, right, we have pressure and volume here. So what I want to do is I want to plot the pressure and volume of my system as I move along the ideal gas, right, at a given temperature. How does pressure and volume vary? Well, they vary as 1 over each other, right? P is roughly proportional to 1 over V. Right, so what I can do is think about now thinking about this process on a diagram where we plot, that's not a right, sorry, where we plot the volume of the system versus the pressure of the system, right? And how does the pressure vary as a function of the volume? Well, it functions as 1 over V. So let me just write a few things here, right? We want to say, well, here's our initial volume, here's our final volume. Let's put the initial volume and pressure right here. And we'll put the final volume right here. Or part, yeah, final pressure. I'm just going to draw some lines to make it nice and pretty. Right, and the way that we connect this point to this point is through a function that looks like 1 over x, or 1 over v. So it's going to have some curvature to it. Right, it's going to look something, let's see if I can do it. Something like this. Right? And so this function is P is equal to nRT over V. Okay? And at a fixed temperature, right? T is fixed here. So T is fixed, right? Because it's isothermal. Right? We have a term for these curves, right? There's going to be one of these curves for every temperature. Right? As I change T, this curve is going to move in this space. right? Because it's P times the constant over V. As T gets higher, this curve is going to push further and further out, right? So there might be, I'm not going to draw it, I'm just going to kind of roughly, right? At a higher temperature, the curve might look like this, and at a lower temperature, the curve may look like this, right? But it still has the same behavior, right? It's still 1 over V for an ideal gas. Right? We have a very specific term for one of these curves. This is what everyone in chemistry and physics calls it. These curves are called, let me just try to put it up here. Yeah. These curves are called isotherms. Right? That makes sense. It's a curve that represents an isothermal process. Isotherms. All right, so now what I want to do is I want to think about the work as I take my system and I compress it. Sorry, this is an expansion, right? Because we're going from VI to VF. VF's bigger. We're expanding our gas. What is the work being done along this curve? Well, the amount of work is being done is the value of the function nRT over V times the change in volume. Okay, so let's say I move the system just a little bit. So let's say I start from here, and then I move it, let's call this V, and then I move it just a slight amount to here to V plus dV. Right, so oh, that's a bad color. I'm sorry, guys. Jeez. I like red. I gotta find a better color. Okay. So let's say I take my gas from here to here. I move it just a little bit, right? So thermal only just moves it very, very slightly. Right? What's the amount of work that's being done? Well, it's the function, the value of the function, the y term here, times the change in V. So if I draw a line segment that's dV long from the initial point, oops, sorry. Uh-oh, where'd it go? Okay, there we go. Right? The amount of work is this value of the function times this. Right? So it's this height times this length. So it's an area. Right? So the amount of work I do in this space is the area of this curve right here. Right? Remember when we calculated the total work or the total entropy, we integrated, right? I'm just doing a little single part of an integration here. Right? So this closed off region right here is the change in work. This is dW. Oops, wrong color again. Right? This little green area is the change in work. Right? And now you can think, well, let me make dV a little bit smaller. Right? Make it so that it's infinitesimally close to V. And then I have a series of those, right? Think about it now, I'm just doing this in steps now. I take now this step, let me just erase this. I just need a little more space, guys. So I take this step at the next step at dV and go another unit dV. And then I create another box. That's a wrong color again. Another box. And then I do another compression step, right, which looks like this.
And there's just like Riemann sums?
Yes, exactly. I'm doing a Riemann sum. Yeah, precisely, right? I'm just recreating an integral here. All right, but I'll tell you why I'm doing that in a second. Right, so I can let dV go to 0 and this becomes the integral, right? Yeah, I'm just doing a Riemann sum. Yeah, you guys know your math well. Right, so work is just the integral over this curve, right? The amount of work is the amount of work that you're doing is the integral from the initial point to the final point. Exactly what I read. We derived earlier. I know that seems, I'm just repeating myself, but what I want to get at now is thinking about what happens to the system when I make dV really big, when I take dV to a much larger limit. Okay, so let me just redraw it one more time so we have a little extra room. I'm not going to draw all these little curves. I'm just going to draw the essential parts. So now what I'm going to do, so here's my isotherm. And I have it from, sorry, I'm going to do this in a different color, from VF to VI. PI to PF. Okay, and now what I want to do is I want my little laborer, I want him to be pissed off, and I don't want him to go slow. I want him to waste. I want him to get it done as quickly as possible, right? I don't want him to be careful if he wants to go home and eat food. He's going to push it really hard, right? So his DV is going to be really big, right? So let's say he starts here, and then what he does is he jams it shut until this volume right here. We'll call this V prime, right? And what's the amount of work he does? Well, it's the area that's subtended by this rectangle. Right? This is the amount of work he does. This is the change in work. I'm not going to call it dW because it's a macroscopic change in work. So it's delta W. And how much work is that? Well, it's all the area under the curve plus this junk right here. Right? If I make dV as small as possible, right, I'm integrating under the curve. There's no hang from the trapezoids on the top, right, from the trapezoidal rule or Simpson's rule or any of the old approximation rules you guys learned, or from the Riemann sum. Right? There's these extra areas here, right? So when he does this and he jams it really fast, he ends up actually doing a little bit extra work right here. You get this extra amount of work right here. Right? This is the extra work he does. Okay, but we just said that the amount of, that in the isothermal process, the amount of work that's being done is equated by the amount of heat. But that's only at an infinitesimal limit, reversible limit. So what he's doing here is he's basically got the reversible part of the work right here being done, but he's adding in this extra bit of energy to it. I shouldn't assume it's gender. I'm assuming that he's all pissed off. He's just like, a dude doing this. That's also appropriate. But anyway, so there's all this extra energy being put into the system. Right? This extra energy is not being equilibrated. Right? This is the equilibrated part of the energy. This is the part of the energy in equilibrium reversibly with the exterior, the bath. So he's adding this extra energy in here, and it's got nowhere to go. Right? And you can imagine he can just keep doing this over and over again, and he's going to end up spending more work. If he does it again, he's going to have another big chunk. He's going to end up doing more work than he did if he just took longer and just moved slowly around it. Okay, so what happens to the gas when he throws this extra energy in? So that's an interesting question, right? Well, where does that energy go? So let's, the idea again, let me just remind you, just drive this point home, is that there is a reversible part of energy. That's this is you could call this the reversible energy, reversible work. And this extra energy on the top is what's called irreversible work. Right? And it's irreversible because the system can't equilibrate with it. It's extra energy put in that drives the system out of equilibrium. Right? The system is only equilibrated up to this curve. So any work done under the curve is equilibrated work. It's able to exchange with the heat, but this extra energy is just sitting there in the system. It's got to go somewhere. Okay, so what happens? Well, let's just look. So what I'm going to do is let's think about how the gas moves as you compress it. Instead of expanding, let's compress. So we're going backwards instead on this curve instead of forwards. Right, so I'm just going to draw it. I'm going to draw my cylinder one more time. That's a really bad cylinder. I have a square tool. Let me just do it properly. Ah, there we go. So I'm going to build 2 cylinders here, one for my irreversible process and one for my reversible one. All right, so this is the first one will be reversible. And the next one will be irreversible. All right, so what I'm going to do is I'm going to take my piston and I'm going to move it slowly in this direction, dV. Move it slowly. All right, and what's the gas going to do as it equilibrates? Well, all the gas, right? So remember, du is 0, so there's all the work being put in is released as entropy into the bath. So what the molecules are going to do reversibly is they're all going to move kind of in an orderly fashion to rearrange themselves in the box. So they're all going to, I'll just draw it. So let's just say like the ones closest to the piston. If we were to draw velocity markers on these gases, right, they're all moving kind of in an orderly way. They have a net velocity or a net flow as you compress it. Right? And any of the excess energy that you have left over that is not needed for this orderly motion, the excess energy is released as heat. So this orderly motion is the change in work. That net motion, right? That net PV motion. Remember, PV motion, PV work is the coordinates of the motion of your gas that have a net like a net direction, right? And so, work in this case is orderly motion of your atoms. All right, so they're just all going to kind of get shuffled in together. Right? This is a very sophomoric way to look at things. It's obviously much more random and chaotic than this, but this is the basic idea. Right? That the gas is moving in an orderly fashion. Orderly compression. Okay, now what happens with my other gas, with my irreversible expansion? Right? So thermohomie is going to apply a macroscopic change in volume instantaneously. It's going to jerk it closed, right? And so some of that energy, right, some of that energy gets converted into orderly motion. Right? So there's going to be some atoms that still compress normally. And I'll just draw 2 layers of them, right? You're going to have a mixture of atoms that move this way. Right? They move that way, but we have that excess energy, right? We have that extra work that the system can't equilibrate, right? The system wants to do this orderly motion and exchange heat to stay in equilibrium, but you're driving it with this extra work that's being injected into the system that can't be equilibrated with the outside effectively. So what's that going to do? Well, it has to go somewhere, right? And so what's going to happen is that those molecules are going to have injected into them some non-orderly motion. That motion is just going to be chaotic, right? So some of that extra energy, which I'll draw with yellow circles instead. So let me just put a couple of layers here, right? That extra energy is going to be contributed into kind of chaotic motion or turbulent motion. Right? You might get turbulent motion from this. Turbulence. Or other what are called shear forces. Right? So when you move, and you might be able to reproduce this. It's kind of hard to reproduce this, but you can do it. I think of a way to do it with gas. You can have a gas you can see. But the idea is very simple. Maybe I'll find a YouTube video. If you take a piston, you compress it very slowly, the gas is just going to do this. It's just going to move very gently, right? The temperature doesn't change, but if you jam it shut, what happens to your fluid? Your fluid, all this extra energy has to go somewhere, so it gets put into these random motions, these chaotic motions, and you generate turbulence and you know, think dissipative effects, right? Think about, another great way to think about this is if you have, this is a similar concept, if you have a faucet, right, and you have of a certain size, water faucet, and let's say you have an insane water pressure, right? And you crack the water a little bit and you get what's called laminar flow, right? You get that nice clean flow of water, it looks crystal clear, right? And the flow is very kind of like a cylinder, a tube-like, right? Everything just kind of does not flying all over the place, it just has this nice smooth flow of water, right? We call that laminar flow, right? And that's the same idea as this. This is laminar flow of the gas as it compresses, right? Laminar flow is flow in a fluid where all the atoms, all the components are moving in the same direction, right? This orderly laminar flow. But if you jam it shut, you introduce this extra energy that can't be equilibrated, it's going to be put into modes of motion that aren't laminar, right? That's the same idea as that when you crank the water pressure up so high that the restriction of the faucet's opening is too small for the amount of pressure, the water flow of your faucet, and then the water just sprays all over the place, right? You get a really nasty flow. You know, there may be little jiggles coming out of it, or what you call them, little sprays. Maybe it kind of looks kind of opaque. You know, kind of looks like a foam almost coming through it, all bubbled up and stuff, right? That's this idea, right? You're putting so much energy into the fluid to flow or compress that it doesn't know what to do with that energy. It can't equilibrate it, so it just puts it into the motion of it just throws it into the molecules in the flow. It just adds as heat, if you will, adds as heat into the cylinder, and then you get turbulence and other types of nonlinear effects, odd nonlinear motions. So that's where that extra energy comes from, right? That when you do something irreversibly, you have to fight these things, right? It's gonna, all that extra energy is gonna get flown into these modes, which resist the compression because things aren't moving orderly, and it requires you to put a little more energy into it to get to the final state. That's that extra work. Okay, so ideally, if you want a nice, beautiful, so what that means is that the easiest way, as in the least energetic way to compress a gas, is to do it reversibly. Right? You want to move smoothly along the curve so that you're not doing any extra work because you're causing turbulence or other dissipative effects in the fluid. Any questions about that? Okay. That's really all I have to say about isothermal expansions. Right? Again, we do isothermal work in chemistry all the time, but the one thing that we really do in chemistry more is, I mean, sometimes we keep temperature constant, but we don't always keep volume and pressure constant. Right? Here we have a fixed cylinder. Right? But when we do organic chemistry, for instance, we rarely do things in fixed cylinders that are sealed. We do them in beakers or flasks that are open to the environment. Right? In those situations, the pressure is constant. Right? If your system is always exchanging with the atmosphere, even if you're building gas up, that gas is allowed to free and the pressure doesn't change. Right? So there are constant pressure. In fact, most chemistry is at constant pressure. You may do it at constant pressure and constant temperature. That's doing an open flask reaction in a hot bath. But sometimes you do what are called constant volume processes, like a pressure cooker. A pressure cooker is a classic example of a constant volume process where you heat something, but you force it into a volume that doesn't move. Right? There's no work being done. The volume is fixed, you're driving heat into it, right? The pressure is allowed to build inside of a pressure cooker, obviously. And when you do calorimetry, for instance, that's usually done in a constant volume way. Right? So maybe we should start thinking about other ways to constrain the system besides temperature, and we're going to find that there are many more relevant, chemically relevant ways to do thermodynamics other than isothermal. All right? We're going to get similar kind of simplifications to our equations in those processes as well. Okay. How much time do we got left? 10 minutes, great. That gives me enough time to introduce the next type of process. All right, and in this class there's going to be four processes that we're going to look at, and they more or less are all the processes that you do in chemistry. Right? And we'll be finished with them on Tuesday. And we'll start putting them all together. All right, the next process I want to think about, our next simplification, is what's called an isochoric process. Does anyone know what an isochoric process is? Anyone ever heard that term before? It's kind of a less common term. But choric means, I forget what it means in Latin off the top of my head. These are constant volume processes. So when we say something that's constant volume, that's something that's isochoric. So this is dV equals 0. Okay. And again, an isochoric, the classic example of an isochoric process is like a rice cooker. Well, a rice cooker's got an opening on top, a pressure cooker. If you've ever cooked in a pressure cooker, you probably know what I'm talking about. If you took a rice cooker and you covered the steam vent, then it would be a constant volume process. Or sorry, no, that's not true. Yeah, that's right. It would be isochoric. Okay, so this is a process where the volume's not changing. Where we have something in a fixed volume, a fixed box, or a reactor, and we're just feeding heat into it. Right? We're heating and cooling it through heat, right? Because there's no work being done, right? If dV is equal to 0, this means that the change in work is 0, right? We're not doing any work. Right? So that means then that the change in the total energy of the system is just TdS, which is equal to the change in heat. Okay? So all the energy that moves in and out of an isochoric system is just heat, pure heat. Now the question is, what can we learn about this process? Right? So let me just draw what it looks like. Right, again, the best way to think of a constant volume process is you have a sealed container. Let's say, for instance, we put a liquid or a gaseous material in here. Here's our material. I'm going to put a thermometer in it. Right, and below it, I'm going to put some heat coils. What do heat coils look like? These are heat coils. Right, so these are generating heat. Right, so dQ in. dQ is coming in, and here we can read the temperature. Okay, so what can we learn about this system, right? How does the energy, and when we apply some fixed amount of heat, right? We turn on our little stove or our oven or a heater and bring some energy into it. How does the system heat up? All right, and what I'm going to show you is that the only thing that we can really say about this system is entirely dependent on the temperature. Temperature tells us everything about this system, right? Because there's no work. We're not measuring volume or pressure. It's completely sealed, and it's constant volume, so there's no work being done. So all of the energy going in and out is heat, And therefore, it's only dependent on entropy and temperature. All right, so what we can say, therefore, that the change in heat, so what I can say instead is this. Let me say this. So what we can say now is that the change in heat is going to be proportional to, this little symbol here means proportional to. I'm going to use this a lot, so. The change in temperature. All right, so we're going to put some heat into the system. And the hypothesis is that that change in heat is going to be proportional to the change in temperature that we measure. Okay. So the way that we can write this, therefore, is we can say that dq infinitesimally, so we make temperature move very, very small, is equal to the change in Q as temperature changes at constant volume, right? It's a constant volume times dt. Okay, and because du is equal to dq, we can say the same thing about u. du is equal to du dt at constant volume times dt. Okay, so we have another linearized derivative equation here, right? We have a line that relates u to t, and it's got a slope, du dt. All right, right. So this is a new intensive parameter, right? We've looked at du ds, du dv, du dn. Right? That gives us temperature, pressure, and chemical potential. So what intensive parameter of our system, the new kind of response of our system, is proportional du dt. Right? This allows us to introduce a new concept, a new thing we can measure. All right, so this function, so let me write this definition. So this derivative, this intensive parameter of the system, the response of the system as a function of temperature, is what's called a heat capacity. So the constant volume heat capacity of a system, and the label that we use for constant volume or heat capacity is C sub V. I'll give that a different color just to drive it home. This is a number, is defined as the rate of change of U with respect to T. Okay, so the heat capacity of a system is defined as the slope of the energy as a function of temperature at constant pressure. Okay, and the units of this are very easy. They have the same, it has the same units of entropy, right? It's energy units divided by energy or temperature units. So the units of a heat capacity are joules per Kelvin. Right? You probably remember heat capacities back in the day. Way back in the day. You probably learned about the heat capacity of water. Does anyone know what the value of the heat capacity of water is off the top of their head? What? It's not 1. You're off by a factor of 4. That's one of these numbers that you learn in Gen Chem and then you forget it because they always tell you. It's CV for water is 4.184 joules per Kelvin per mole, for instance. All right, so what does that mean? Right, so let's remind ourselves what a heat capacity means. It means that in order to increase the temperature of a mole of water by 1 degree, you need to put in 4.184 joules of energy. Simple as that, right? It tells you how much energy the material can absorb before the entropy kicks the temperature up another degree. Right? Remember that the system has all different ways that it can take that energy, and the more ways it has to take that energy, the higher the heat capacity is going to be. If it runs out of ways to do that, it's going to put it in as entropy or heat, and it's going to jump to make the temperature go up. Right? So some materials have a very low heat capacity, some have a very, very high heat capacity. Right? Some things are really good at thermal insulating heat. Some things are really good at transmitting heat, and those things relate, of course, to heat capacity. Okay, so we'll just leave it there for now. Okay, so we'll come back to the heat capacity next class, look at it a little more carefully, see what we can do with it, and what we can learn from heat capacities. All right, have a lovely weekend, everybody.
Oh, also, I saw the email. So for meeting times on Mondays, I actually could also come before your 2
Oh, then
o'clock
just come at
class
1:30 then.
Okay, because
That would be great.
my CLR hours end at 1, and then I normally just go over to Eklund anyway, because my class is in Eklund at 2, so.
Then come on over then. Just come when you're done then.
Yeah.
You can hang out in my office for 45 minutes, I don't really care.
Sounds good.
All right, cool.
It's easier than finding a place to sit on campus for an hour, because
Yes.
it's so busy, and Eklund is nice and quiet.
Yes, yes it is.
Next Tuesday, can I come late to class? Okay, I just have to do training for a certain instrument, and the professor's only available
That's
in the
fine.
afternoons, and I only take class in the afternoons.
problem.
Okay, thank
No
you so
problem,
much.
Abby. Yeah, no, of course.